My name is Lynn Krasinski. I'm a forensic chem and MB3 undergraduate at Towson University, and I will be presenting today on my ferrofluid project. A quick introduction to ferrofluids. They are colloidal suspensions of magnetic nanoparticles, which basically means very small magnetic particles suspended, even like monodispersely, in liquid. They have unique physical and chemical properties because of their size. They have many applications. They were actually originally synthesized for their use as jet fuel for their ability to orient in zero gravity, but now are focused more towards biomedical applications, and such as MRI imaging, contrast agents, magnetic drug targeting, and hyperthermic cancer treatments. And we achieve most of the applications that we'll use for this ferrofluid by functionalization, which is basically modifying the surface of these nanoparticles. As you can see here, when we add our gold coating, it's increasing our particle diameter as we would expect. I don't know how to describe these though.
The average is 17 nanometer in diameter with a standard deviation of 6.
So should I go through each of these values?
No, just one is enough. So like you said, right, the smallest that you were able to achieve is the iron cobalt nanoparticles, which was 17 nanometer in diameter.
So just saying.
And it becomes largest when you have gold coated onto it. So you can say like that for this slide. When you are talking about the gold, don't say you're adding gold to your project, you're adding gold to your product. So you see the references you have are good, you put them down to under each of those pictures, but make sure the font size is the same Arial font that you used on the right hand side and the same format. Okay, so
yeah.
Here you have author and the title and the year, right? You should have the journal article more than the title, right? What's more relevant is the volume number, page number, and the journal article. Okay.
So I just need to add this part.
Yes, you need to add that part to that and do it. And then always remember, I know you asked me and then you described that whenever you put something on a slide, right? Make sure you point to that and explain what it is. That don't just put it for the sake of picture's sake.
Good afternoon. My name is Nicole Hundra-Giannis. I'm a junior biology major attending Towson University. Today I'll be presenting chromophore ligand exchanged gold 25 nanoclusters, specifically their optical and electrochemical properties. I'm presenting from the Department of Chemistry at Towson University under the mentorship of Dr. Mary Devadas. So to begin, what is a gold 25 L18 nanoparticle? Gold 25 is a nanoparticle that consists of 25 atoms of gold. There are 13 core gold atoms displayed here in the schematic to the right. 12 gold atoms are contained in an orthogonal bridging semiring. These 12 gold atoms in these orthogonal semirings are bridged by my organic ligand hexane thiol, which stabilizes my gold cluster. Hexane thiol is shown in the bottom left. Displayed in the middle is the same gold 25 L18 core stabilized by the ligand hexane thiol. This ligand stabilizes my core by making use of the hard-soft acid-base principle, which is essential for my reactions.
Okay, so we got to time this appropriately. Okay, so then we'll see whether we want this outline here. And remember, I don't like to see a slide with no picture on the right hand side. So you have space. So if you go with the outline side, kind of have either a cartoon or a crystal structure, like a real XRD image,
Yeah.
right, from the paper and publication onto the website, and the gold 25 there is not in Arial font. Okay. So up to the now slide number 3, there is a slide number, but then when you go to the next slide, right?
Yeah.
There's no slide number after that. So put that on.
Okay.
Okay. And when you talk about gold 25, you always refer to it as a nano cluster. Okay, because it's still in the cluster regime, because it's still like a molecule behavior.
Okay.
When the nanoparticle becomes larger than 10 nanometers, 100 nanometers, right, then it's becoming more like a metal. So when it behaves and shows these metallic traits, then you most commonly call it as a nanoparticle. But the structure that and the size dimension that you're working with, you've got to change the title of the slide nano cluster. When you are discussing this, we got to go through a little more about the scientific terms that you use. For the next slide, go to the next slide. Actually, that's where you come up with the. What was the next slide? 12.
Well, it was this side that I talked about the orthogonal submarine staple motifs
Okay.
and the bridging gold core to make the 1325.
Right. So yes, you're talking about the gold core and the 13 gold cores, and then the orthogonal rings, which have the mixed gold ligand in it, right?
Mm-hmm.
So there was something that you mentioned that was kind of off. So maybe when you practice the next time, I will catch it exactly what you said.
Because I want to refer to something about the staple motifs, the sulfur, the hydrogen bonding, and then I transition to the hard soft acid base principle, which accounts for the increased stability of these clusters.
Okay. And I don't remember exactly, but there was something off about the orthogonal staples. Because you said, I think later on when you talk about the chromophore exchange, you said that all those staples are replaced. It's not the staples that are replaced, it's a thiol in that staple. Okay?
Okay.
You said it modifies the core. It doesn't modify the core. Yeah, that's what.
I said that the hexane thiol modifies the core?
No, the orthogonal staples, when you replace them with the chromophore, right, it changes the core. It doesn't change the core. Yeah, but yes, it doesn't. So when you were saying it, you said core. So just correct that. Just remember that.